Okay, well, good morning, everybody. It's a good thing we don't have to leave our homes, isn't it? There's snow flurries, it's cold outside. Hope everyone is well and healthy, and your families are doing well. Today we will talk about the last part of this VSEPR theory. And then I guess as time allows, we'll start talking about what's called valence bond theory, or a little more details of what orbitals overlap when you're forming covalent bonds. And again, what I consider really, really fundamental, important topics in chemistry, because this really, whatever we're talking about here, these shapes of molecules, that's what we really pick up on in Chem 132. And so we start to talk about, how do individual molecules attract one another, and so intermolecular forces. All right, so this is what we did yesterday. Let me just kind of give you the quick rundown here. So we talked about um, molecules with two electron pair domains, or charge clouds, as they're referred to in the PowerPoints. And this is if you have a central atom and two things bonded to it. And I called that AX2, and the geometry was linear. Okay, so 180 degree bond angles here. And then we looked at three electron pair domains. And so there were two varieties of those. It's the one where you can have three things bonded to a central atom, or AX3, and that's trigonal planar. Okay, so it's all on the plane of this paper. Okay, and the angles are 120 degrees. And then you can replace one of the x's with a lone pair, and that is, I called it AX2L, and the geometry is bent. And remember that this lone pair takes up a lot of space, and so it's going to repel these bonding electrons. And so the angle is going to be a little less than 120. Okay. And for the exam, not for next week, but on the final exam, you should have an idea about these angles too. Again, I'm not going to ask you like the exact one here, but you should know that it's less than 120. Okay. And then we looked at, the last one was with four electron pair domains. And so if there are four things bonded to a central atom, then it was AX4, okay, and that was tetrahedral. And all the angles are 109.5, okay, so that's a number you should, like, not exactly, like right around 109 degrees, you should kind of have that in mind for the final. And then if you replace one of the x's with a lone pair, then that's going to be trigonal pyramidal. Okay, so this is like a tripod type of shape. Okay, and all the angles are going to be less than 109.5, again, because of this repulsion effect. And then AX2L2, like water, for instance, is our good example for that one, where you have two lone pairs. Now you've got a lot of repulsion, and that angle is much less than 109.5. Okay, and so according to these molecules, if it's ammonia, it goes from 109.5 to 107, and then water, it's 104.5. Okay, so a fair degree, quite a bit of difference there, like 5 degrees difference. Okay. All right. So any questions about those first sets of molecules? Okay. I've got some Chem 101s to give you an idea of what questions to expect kind of on exams. So we'll get into those after we finish all these shapes here. Okay, so the next one is if you have 5 electron pair domains, Um, okay, and so the first variety of that is if you have this one, where I call it AX5. Okay, and as this is probably showing a lot better than I can draw it, these blue ones, does everybody see these blue balls here? Or these are the atoms, three of the atoms that are bonded to the central atom. These, you can think of it as they're on the plane of my paper. Okay, so maybe this one shows it a little better, the top view. So these three are on the plane of my paper or your computer screen. And then you've got two atoms that one is coming out at you and then one is going in behind your screen. Okay, so those are these two. Okay, so this is called trigonal whoops, if I could spell, bipyramidal. Okay, and so the reason it's bipyramidal is because if I draw it kind of like this, where again, those three are on the plane, and then sometimes we'll draw it like this, where, you know, this is kind of bolded, meaning that that's coming out. And then this back one, we'll draw it as kind of a dashed line like this, saying that that's going in behind the paper. Okay, and you can draw little pyramids, you know, like that would be one pyramid, and then that would be the other pyramid. Okay, that I kind of really just made messy here. But I guess this is probably again better. Okay, so if you have the central atom, and then these are those three that are on the plane, that's the one that, I don't know, is coming out at you. That's the one that's going in behind. And so it's kind of showing, right, that you've got a pyramid this way and then a pyramid going down. Okay, so trigonal bipyramidal. All right, so now this is the fun ones. Okay, so what happens if you replace one of the x's with a lone pair? Okay, and so the ones that you start to replace first are these blue ones. Okay, so these are the ones that will first be replaced. And so if I draw it like this, whoops. Okay, so, well, let me do this again. That's cleaner here. Okay, so it's coming out. That's going back. Okay, so that's your trigonal pyramidal. Now what I'm going to do is replace this one on the right with a lone pair. Okay, so that's the first one that will be removed. Okay, so it's like that. Okay, so this is your AX, what is it, 4L. Okay, and this shape, it's kind of funny that it really doesn't have a scientific term. Oh, I don't know. Let's see. There we go. So to best illustrate this, let's kind of rotate this structure 90 degrees counterclockwise. Okay, so kind of to this. And so that means that we've got x's there, we've got x, x, and like that. Okay, and so this shape, does it remind you of anything maybe from childhood? So if you had, you know, this kind of thing going on, right? And then, you know, you're standing here, someone else there, okay? This is like your teeter-totter. Well, this shape, it's called the seesaw shape. Okay, so it's nothing more scientific than that. Okay, so that is the case if you have, again, AX4L is called seesaw. Okay, and so that's what that looks like. Okay, and so as far as angles go, when we looked at this AX5, that and that is kind of our basic shape. These angles on the plane of the paper, those are all 120. Okay, so it's like you have a trigonal planar unit, like we talked about yesterday. Okay, so those are all 120. And then between this and this, so between the page or your computer screen and the one coming out at you, that's 90 degrees. Okay, so again, I think that's better here. Okay, so all these are 120, and then this angle here and this here, this is 90 degrees. Okay, and so then when you look at this structure, now you're going to have 180. Okay, so this angle here is going to be 180. And then you're going to have 90 degrees between here. Okay. And then what do you think the angle is going to be between these ones? So this, and this. Okay, or I guess this one right here. What do you think that angle is going to be? Any ideas? So it used to be 120, right? So this angle in just the AX5, so this one here is going to be 120. So what do you think it is in this shape here? Still 120?
Less than 120, that's for sure.
Yep. So exactly, it's going to be less than 120 because you got this big lone pair that's going to repel these bonds. So remember, this lone pair is on the same plane as these two fluorines. Okay, these two are on a different plane, but these two are still on that same plane as the lone pair. So it's going to force these down a little bit. Okay, so that angle is going to be less than 120. Okay, so you really have like 3 different types of angles for the seesaw shape. Okay, so you've got linear kind of here, so 180, 90, and then less than 120. Okay. All right, so then if you replace a second one with a lone pair, it's going to be one of these ones. Okay, so this is the next one that's going to be replaced with a lone pair. Okay, and so it'll look something like this. Okay, and so this one's kind of easy to see. So that's called T-shape, right? Because it forms a T. Okay, so T-shaped. Okay, looks like this. Okay, where you've got a lone pair there, and so this angle will be 90, that angle will be 180. Okay, so you've got 180 here and then 90 degrees there. Okay, and so that would be our AX, what is it, AX3L2. Okay, 2 lone pairs, 3 things bonded to a central atom. Okay, and then the other one is if you replace all 3 of those that are on the plane, that form that trigonal planar unit. Okay, if you replace all of those with lone pairs. Okay, so now all 3 of those are lone pairs. Okay, so now you've got AX2L3. Okay, so this one was, again, T-shaped. This one is just going to be linear. Okay, because the only angle you have is 180 degrees now. Okay, so it's just linear. Okay, so these are some examples like ClF3, and then the triiodide anion is linear. Okay, All right, so any questions about those then? So all those are still considered 5 electron pair domains. Okay, so the difference, this is one thing, like on your final, and I have one Chem 101 question about it today, just to give you a flavor of that. But the difference between charge clouds or electron pair domains, on exams, I'm going to keep it, the verbiage talking about electron pair domains, because I think it's a little better term. I don't know about charge clouds. So 5 electron pair domains. So these domains refer to either these lone pairs or bonding pairs of electrons. Okay, so all those refer to electron pair domains. But your shape, sorry about that. Your shape is all related to really like how many atoms are actually bonded. And then, these lone pairs influence the shape. Okay, so your shape is T-shape, but you still have a trigonal bipyramidal electron pair domain. Okay, does that kind of make sense? Okay, so just to kind of say that, so if we have this one, AX3L2, okay, it's still a trigonal bipyramidal electron pair domain, okay, but its shape is T-shaped. Okay, so this refers to electron pair domain is still, 5, okay, but its shape is different. Okay, well, sorry about that, everybody. The WebEx audio server quit on us, and so WebEx is looking into it for us so it doesn't happen again, hopefully. So I guess I was cutting in and out, so I'm not sure what you heard, but you can look at a variety of different kinds of shapes. You can go all the way up to 10 atoms bonded to a central atom and get into all those different shapes. If you go on to take chemistry 331, you'll get into more of those. And for this class, though, we will only consider up to 6. Okay, so I'm sparing you a lot more details. And this one, so what is this, the 5th? Yes, so the 5th variety here is 6 electron pair domains. Okay, and this one looks like this. Okay, so our AX6, in other words. 6 things bonded to a center. This one, one way to think about it is as shown on the PowerPoint, where you've got these 4 on the plane of my paper or on your computer screen, and then you've got this one coming out at you, this one going in behind. Okay, so that would be this kind of top view. So these are on your computer screen. This one is coming out, and then you've got one that's going in behind your computer screen. Okay, and so this one is really easy with angles. Every one of these angles is 90 degrees. Okay, and this is called an octahedral shape. Okay, and the reason why it's octahedral is because it's got, it forms an octahedron, I guess. Okay, so if this is your center, and this is what it looks like kind of in 3D. Okay, so these are those 2, kind of coming out at you, going in behind, and then you've got those 4 that are on that plane. Okay, so this is an octahedron shape. Okay, so then when you start to replace one of these with a lone pair, kind of the easy way to think about it is, if you put it like this, and then it's one of these that's going to be replaced. Okay, so that is shown here. So that's your octahedral. And then let's just replace this one with a lone pair. Okay, and so now you're going to have a square pyramid shape, right? Because it can form a pyramid here. Okay, so to think about it is like this first. Okay, and then we're going to say that's the one that goes away. Okay, and now you've got a square, so our AX5L is square pyramidal, or square pyramid. Okay, and again, it's pyramid because you can draw kind of a pyramid from all of those ones up. Okay, so from this plane up to there is a pyramid. Okay, so as far as angles, I guess you would say, all these angles are still going to be 90. Okay, they're on a different plane than that lone pair. And then this lone pair is really not going to influence, that x. And so really all these angles are still going to be 90 degrees. Okay, so even though it's square pyramidal, it's all still 90. Okay, it just has to do with what plane this lone pair is on. Okay, and then the last shape, finally, you're thinking, is if we replace two of those originally with lone pairs. Okay, and now it's square planar. Okay, so that means it's just on the plane of your computer screen, and all these angles are still going to be 90 because these lone pairs are on a different plane. Okay, they're perpendicular, and so all angles are still 90. So AX4L2 is square planar. Okay, and all the angles, so it's just like this, all the angles are still 90. Okay. All right, this is actually a really important geometry or shape for application. So this is one. I guess this one. So this is called cisplatin, which actually just down the road, it was discovered, MSU. And this is a really important cancer drug. And so this is used to treat a variety of different kinds of cancers. Cis refers to substituents like chlorines that are on the same side of the molecule. Okay, versus, you're going to learn this in organic chemistry, but that would be trans. Okay, so this would be, they're isomers, okay, which means just different rearrangements. Cis means they're on one side, trans means they're on opposite sides. Okay, so kind of TMI for this class, but this is another example where you've got a square planar geometry. And it's actually that geometry that helps it attach to cancer cells, okay, because this is wide open here. You'll notice this shape, you've got a lot of room above and below. And so that has it really easily attached to cancerous cells, okay, and then deliver, its anti-cancer behavior. Okay, so this next slide, or a couple slides, because there are a lot of them, summarizes all the shapes that you have to know. Okay, so if you have two bonds, no lone pairs, that is linear. Okay, and there's a geometry, CO2 for instance, or beryllium dichloride, that's another one. Then in the electron pair domains of 3, you have two varieties. You've got one where you've got 3 bonds, no lone pairs. That's trigonal planar. And then you've got the one where you've got 2 bonds, 1 lone pair, and that would be bent. Okay, like SO2. And then you've got with 4 electron pair domains, you've got the ones where no lone pairs, that's tetrahedral, and most hydrocarbons. Okay, so hydrocarbons just mean that they're composed of carbon and hydrogen. Okay, so all of those, the central carbon, most of the time will be tetrahedral. Okay, so very, very common geometry in organic chemistry. And then if you have 3 bonds, 1 lone pair, now it's trigonal pyramidal, like tripod, think here. And then if you have 2 bonds, 2 lone pairs, it's bent. Okay, and so we did that last lecture. So the new stuff from today are these ones. And so if you have a 5 electron pair domain of 5, so just bonds without any lone pairs, that's your trigonal bipyramidal. And then you start to replace, for instance, this one with a lone pair, and it becomes seesaw. Then if you replace another one with a lone pair, now it's T-shape. And then finally, if you have all lone pairs on that plane, the trigonal planar plane, so all you have then is linear. Okay, so it's with 3 lone pairs and 2 things bonded to a central atom. And then with 6 electron pair domains, if you don't have any lone pairs, it's octahedral. Then if you replace with 1, it is square pyramidal. And with 2, it's square planar. Okay, so that is it as far as shapes go. I have some Chem 101s that are up. If you watch this video, within the next little while, they'll be open for you. I'll also try to, if I can, put them to homework or something so you can look at them or do them later, so you don't have a time limit. And so, I don't know, maybe the best strategy is let's go through these. Okay, so VSEPR 1. Okay, so not many people have looked at this yet, but acetyl nitrile. Okay, so acetyl nitrile, again, for these questions, when I'm considering shapes of molecules, if I ask what is the shape or what angles does something have, that means draw the Lewis structure first. Okay, so for this one, acetyl nitrile, okay, you have to count how many valence electrons. And so we've got 4, 1 times 3 for hydrogens, another 4, and then another 5. So what is that? 9, 10, 11, 12, 16 valence electrons. And so then you put your bonds here. Okay, so you have hydrogens bonded to the carbon, and then you're also going to have a carbon and then a nitrogen. Okay, so on an exam, if I give you this one, I'll kind of tell you how to rearrange the atoms in there. Okay, because this one is kind of not so clear. Again, usually this one on the left is a central atom, and so it is. Okay, and then you've got 3 hydrogens, and then this CN group kind of attached to it. Okay, so we've now placed 2, 3, 4, 5, 6, 7, 8. We've placed 10 electrons. We can't place any more around the carbon on the left, and so let's start building up around the outside. So let's maybe do 12, 13, 14, 15, 16. Okay, and then you say, well, this one doesn't have an octet, so then let's do that. And we still need electrons, so let's do that. Okay, so that would be, if I get rid of my squigglies here, okay, that is the Lewis structure, okay, for acetyl nitrile. And then it's asking geometries. And so around this carbon, you have 4 things, no lone pairs, so that would be tetrahedral. Okay. And then around this carbon, I guess all you have are 2 things bonded to it, right? So this would be like your AX2. Okay, no lone pairs around that carbon, so that's just linear. Okay, so the 2 geometries will be tetrahedral and linear. Okay, so one person had it. This was kind of the wrong structure here, but yeah, tetrahedral and linear. Okay. So again, you know, everybody, just because of this whole fiasco, COVID-19 fiasco, you will get your 3 points for participation. So don't worry about, you know, if when you try these questions, they're not available anymore, if they've expired. Don't worry, you're still going to get your participation points. So, okay, so VSEPR 2. Okay, so arsenic tetrafluoride. So to get the valence electrons, so we've got 7 times 5, so that's 35 electrons. And then arsenic has another 5, so that's 40 total. So let me kind of just draw this around. Actually, let's put it in as this first. Okay, so 5 things around it is usually like that. Okay, and so we've now placed 10, 16, 9, 40. Okay, so no lone pairs in the center. Okay, and so in this case, we've got, it's called, so AX5 is trigonal bipyramidal. Okay, and so our angles here are going to be 120 on that plane and 90 on that plane. Okay, so 90 and 120. All right, VSEPR 3. Okay, BR3 minus. Okay, so that's 7 times 3 is 21, and then another 1 for the charge. 22 valence electrons. So that's 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. So this would be like our AX2L3, okay, or it was related to 5 electron pair domains. Okay, and so now it's just going to be linear. Okay, so electron domains and molecular geometries, yep. So its electron pair domain is still going to be trigonal bipyramidal, okay, for electron pair domain, but its shape is linear. Okay, so this is a good example of both of those concepts in a question. Very typical of what you might see on the final. Okay, so VSEPR 4. Again, a similar kind of question. So ICl4 minus. So now you've got 35 plus another 1 is 36 valence electrons. So let's first just draw the Lewis structure, not really paying attention to how we're putting them around here. So we've placed 8, 14, 30, 31, 32, 33, 34, 35, 36. Okay, so electron pair domain. Okay, you have a central atom surrounded by 6 things, whether it be bonds, so 4 bonds and 2 lone pairs. Okay, so that tells you that it's an electron pair domain of 6. In other words, octahedral. Okay, but its shape is square planar. Okay, so this is correct. Yeah. And then the last one, VSEPR 5, is, okay, so it's showing you IF4 plus. Okay, and then predict whether that angle A is going to be equal to, greater than, or less than the ideal bonding angle. Okay, and so the ideal should be, if you had this kind of situation, okay, with, like, we'll just say these, so 5 things around it, this angle should be 120. Okay, just like that one, or that one. Okay, but as soon as you replace this with a lone pair, if it's on that same plane, it's going to repel those electrons. Okay, and so now it's going to be less than 120. Okay, these are going to move in a little bit like that. Okay, so it should be C less than. Okay, and most people got that, well, so far. Okay. All right, so the last bit of today, let's move on to valence bond theory. So this is really the simplest theory to describe how are electrons paired, or electrons shared in forming a covalent bond. And so, for instance, in H2, hydrogen, all we have, so as far as the valence electrons, we just have a couple. So if we look at the hydrogen atoms, all they have are 1 electron sitting in a 1s orbital. Okay, and so these can pair up, okay, as shown in the slide. Okay, so 1s orbitals are these spheres, and so we pair them up. So we've got an electron spin up, and then the other can kind of spin it down so that those electrons are paired, and it forms a bond. Okay, you've got 2 electrons in between those 2 hydrogens. Okay, so if you have kind of head-on overlap of these orbitals, it's called a sigma bond. Okay, so head-on orbital overlap is sigma. And so if you have s orbitals, so an s plus an s, in other words, like this, 2 spheres colliding, that will give rise to a sigma bonding orbital. Okay, but you could also have p orbitals. Okay, and so you could have this kind of situation where they can overlap like this. Okay, shown here. Okay, so now for fluorine, you can have a 2p orbital that kind of overlaps head-on, and that is also a sigma orbital. Okay, so if it's in kind of the same plane as where these fluorine atoms are, then we call it sigma. Okay, and so this is another type of sigma bond if you have overlap between 2 different types of orbitals. And so between a 1s of hydrogen and then the 3p of chlorine, for instance, okay, because that's its valence electrons, remember, are in the 3p. And so you can overlap that, okay? And so this would be a sigma bond, okay? So in HCl, that would still be a sigma bond, okay? So just kind of some definitions here. So covalent bonds are formed by overlap of atomic orbitals, okay, and each of which contains 1 electron of opposite spin. And so each of the bonded, so this is this theory. There are other more complicated ways to describe bonding. So this is the most simplified version. Okay, and so you've got just these simple atomic orbitals overlap, and then they each share one electron. And then each of the bonded atoms maintains its own atomic orbitals, but the electron pair in the overlapping orbitals is shared by both atoms. Okay, and so that's just really saying that once you have formed this bond, okay, now this electron pair is shared between these two atoms. Okay, so these electrons are free to move around in between here. Okay, and so the greater the amount of overlap, the stronger the bond. Okay, and so that's what I was showing you. One of the periodic trends is, you know, for instance, if you have HF, okay, where you've got kind of small little orbitals there. So you've got like this. So that's a 1s, and then that would be your 2p overlapping versus HI, okay, where you've got a 1s of that size, and then what is that? Your iodine would be 3, 4, like your 5p orbital, okay? That overlap is not as strong, right? So it can only overlap kind of just in this area here. And so this is a weaker bond. Okay, so as you go down a group, the bonding, covalent bonding, is weaker. Okay, so and that is just weaker overlap between bigger orbitals. Okay, so let's look at, well, you know what? Let's stop there. Okay, I want to, for you to be able to ask questions during hybridization, so this next topic. And so we will cover this either Monday. So what I'm planning for on Monday, that's the day before your exam, so I'm going to take questions related to, you know, the previous content. So I'll let you ask questions about the practice midterm or any topic you want related to the exam. If there's time, then we'll continue talking about hybridization. If not, then we'll cover this, I guess, the week after. Okay? All right, so that is it. Again, I apologize for the WebEx problems today. It's out of my control, but hopefully this all made sense. And as always, you know, send me an email if any of this you'd like more clarification. All right, enjoy the rest of your day.